Hi, everybody, and thank you and welcome to this third session of the LT-Brits webinars. I'm sharing the screen. I hope that you can already see it. Okay, so yeah, today the main topic will be neural machine translation. And as you see in the title, I will go through unsupervised, supervised, multilingual, self-supervised. So a lot of kinds of neural machine translation with the idea that we see how they can be applied to the low resource setting. So it's not going to be a deep dive into any of these, but just the ideas that can be used and extracted for the low resource setting. And this is something that we already started in the last session. In the last session, we talked about cross-lingual embedding during a lot of time with the idea of being able to understand and to explain unsupervised machine translation. So the first thing I will do today is just summarize what we did in the last session and see how unsupervised machine translation performs in the low resource setting. Then I will introduce supervised neural machine translation, so something that we haven't done in 2 sessions. So maybe it's time that we already know how it works and also how it's performing in the low resource setting. And as a trivial extension to that, we will see multilingual neural translation. And multilingual neural translation will be used to introduce also self-supervised neural machine translation, another kind of architecture that is quite useful in the low resource setting. As you see, these are lots of topics, and my idea is that we will do last in the last session. So the third topic is not going to be covered completely. We will see some of the basics, and in the next session, I will start by summarizing these basics and then go into the low resource setting. But yeah, also as in the last session, I realized that I want to explain lots of things. So the thing that happens is that I start talking and I really don't shut up till the end of the session. And we don't have time for questions if I do this. So please just unmute yourself and interrupt me during any time in the talk so that we can discuss, comment things or answer questions in the middle of the talk. I don't mind it at all. So yeah, let's try to make it a bit more interactive because I fear that I will do the same as last time and I won't have the 10 minutes at the end for discussion. So let's do it in the middle if it's fine with you. Okay, so maybe I can start by summarizing last session. By the way, one thing I also want to know, I don't see the comments in the chat while I'm talking. So yeah, if you say anything, just go direct and interrupt because I don't know if it's a Linux thing, but I'm not able to see anything else while I talk. Okay, so yeah, now, yes, I'm starting with the summary finally. So last time we were talking about unsupervised machine translation. And we saw that there are 2 main approaches to initialize the system, which is really the most important thing in the unsupervised setting, having a good initialization. So we can initialize with cross-lingual embeddings or with pre-trained multilingual models. What we saw was especially the case of cross-lingual embeddings, and we really saw a lot of examples on how to do high quality or at least the best quality that you can get in the low resource setting for cross-lingual embeddings. We saw that there are 2 main ways to get them via supervised training or unsupervised training. With supervision, you can apply joint learning or mapping. And then most of unsupervised techniques are based on mapping. But the line between mapping in supervised embeddings and unsupervised embeddings is really very thin because you can map embeddings with very small dictionaries. And this is something that at the end is very close to unsupervised setting. We talk about the importance of isomorphism on embeddings. So for machine translation or in multilingual settings, what you want to do is have all the languages, or at least the 2 languages in the same space. To do this, what you need mainly is to have 2 language spaces that are isomorphic to each other. That means that you can project one language into the other one or the two into the same space, and they have a similar characteristic. So this is what is shown in this picture, and that means that one language can be mapped into the other language just with a linear mapping. Getting the mapping was not technically very difficult. We saw that all you need to do is solving the Procrustes problem that has this isomorphism assumption as basic hypothesis. And solving this problem gives you the best matrix that does the projection from one language into the other. We also saw several problems that might have multilingual embeddings or cross-lingual embeddings. One was that this isomorphism might not be true for distant languages. And the other one was that embeddings, being high-dimensional entities, have what is called the Hypness problem. That means that there are some words that are really close to lots of other words. So they are like hubs. So it's difficult to get a translation for these words because they are really close semantically to all of other words in another language. To solve this, we saw that better than using the standard cosine similarity measures for embeddings, it's good to use margin-based similarity methods that take into account that some regions of the space are really more dense than they should be. So the main pipeline for obtaining cross-lingual embeddings via mapping was the first thing we needed is high quality or the best quality we could get for monolingual embeddings. Then we would use a small dictionary. We are assuming supervised setting here. And with this small dictionary and the monolingual embeddings, we will learn a projection from one language into the other. We would do this solving the Procrustes problem. And then when we have all the embeddings in the two or more languages in the same space, we can find the translation of one word in one language, just looking at the closest word in the other language. And we will be doing this using this margin-based similarity measure to see which words are close to each other. And that was all for getting cross-lingual embeddings in the supervised setting. And we also saw that it was very close to what we will be doing for unsupervised embeddings. In the case of unsupervised embeddings, we wouldn't have the initial dictionary. So we would need to induct and to learn from scratch this seed dictionary at the beginning. Something to remember is that dictionaries really don't need to be that big. So for instance, 20, in the examples Mikel Artete showed here, he was getting quite acceptable results with dictionaries with only 25 words. And also just using numbers that are the same in two languages, they share the script, the results were also quite promising. So, and the distinction between supervision and non-supervision here is very light because with very small dictionaries you get good results, and being able to induce small dictionaries was not that difficult. So we saw several techniques to be able to induce these dictionaries. And then this had a clear application for unsupervised machine translation. So unsupervised machine translation is based in three big principles, in three big methodologies that one follows. One is a strong initialization, then denoising, and then back translation. The initialization is simply done at word level. So if we have one sentence, the way to initialize the sentence can be just with these cross-lingual embeddings that we have, just an average over all the word that has a sentence. So we already know about the initialization. We can use the cross-lingual embeddings, supervised or unsupervised, to initialize an unsupervised neural machine translation. And then we need a combination of denoising and encoders and back translation to perform the translation. What's the meaning of each of these modules? So denoising is quite simple. You learn representations of sentences just by modifying a sentence in one language, adding some noise. Noise can be swapping the order of words, removing a word, adding another one. So small things that make your sentence slightly different, and trying to force the system to learn the original sentence, the one without this noise. This is a denoising encoder. And for back translation, the thing that we wanted to do is to use at each point of the training the current status of the system to translate the sentence in one language, then back translate it again to the original language and see the difference between the translated and the original sentence. And we would like this difference to be as small as possible. So this is the combination of the two things that we are doing in unsupervised neural machine translation. Back translating sentences with the current system and minimizing differences, and forcing the system to learn a good representation in a monolingual way for each language via denoising and encoding. This can be done in very different ways. So it's clear that you need representation for the languages involved. In this example here, you would need representations for French and for English. So you would have encoders and decoders in French and in English. And then this will be used to do the denoising and to do the back translation. You can have several encoders, one encoder per language, one decoder per language. You can have a shared encoder for all the language and a shared decoder for all the languages. You can have different encoders with shared attention. There are really lots of possibilities to build architecture, but at the end, with all of them, what you are doing is this combination of denoising autoencoders and back translation. We saw the details quite deep last time, so yeah, I'm just adding here this slide to remember the point where we were last time. And the last thing that we did is look at the performance of these architectures. We look how we can translate using unsupervised neural machine translation with respect to what we would do with a similar system trained on parallel data with supervised settings. We see this example here where the translation task was going from English to French and from English to German, so two very high resource language pairs. We saw that translation quality for these languages in the supervised setting is really very high. So we get Bleu scores. I haven't said that this table is with Bleu scores above 40 for English, French, and yeah, even more than 30 for English, German. When we apply a neural machine translation, we see that the translation quality is lower. So remember that we are not using any parallel data here. So all the parallel combinations and learn on the fly. So there is no parallel data and translation quality diminishes a lot. But then besides neural machine translation, there are systems that combine also statistical machine translation modules. And with this combination, translation quality increases a lot. It's not at the point that we have for supervised machine translation, but it's getting really, really very close. And what's the reason of this? So the main reason is that statistical machine translation is not an end-to-end architecture. So it has several modules. We have the language model, we have reordering, we have translation table. So there are different modules, but most of them are really monolingual. So the monolingual modules will be already high quality, and you only need to worry about translation tables at the end for statistical machine translation. And that is quite a direct application of cross-lingual embeddings, again, getting this translation table. So this is why statistical machine translation really performs better than neural machine translation in this case. And with the combination of both approaches, one can be really close to supervised settings. In some cases, we are even above supervised settings because we can have more monolingual data than parallel data. And this is what we saw already last time. And what I also wanted to notice is that, yeah, this is what we get with unsupervised neural machine translation with word embeddings, but current state of the art of unsupervised system use pre-trained language model for initialization. And this is getting very, very close to supervised setting or even getting better performance in all cases. And this is something we will see in the next session, how to use pre-trained language model, this huge pre-trained language model in all the machine translation architecture that we will be seeing today. Still, as you see in one of the test sets on the right, the leaderboard for unsupervised machine translation is still this combination of unsupervised statistical machine translation with neural machine translation given in RTHs and RTHs. But at the end, what we want to see if we can use these technologies for low resource machine translation. That is one of the problems that we want to address in this webinar. So can we do it? And the results that I have shown you don't use parallel data. All, of course, is unsupervised, but they really use a lot of monolingual data. So the trainings that I have shown here were using NewScroll. And NewScroll for these languages has more than 1 million tokens. So yeah, more or less, it's more than 2 million tokens in English, a bit less in German, and less than 1 million in French. But that's really a lot of data. So it's data that we don't really have in the low resource setting. So unsupervised neural machine translation seems to be working well, but it's working well in a case that we in principle don't need it. If you have this amount of data, it's easy that you also have some parallel data. And if you have some parallel data, don't really go ahead with the simple thing, right? You don't need to do this complicated thing. So what we'd like to do is really make unsupervised machine translation work in the cases when you only have monolingual data, and this monolingual data is not as large as we can see now. So one question we can ask ourselves is, when is this unsupervised setting working? So can we use it? Can we use it always? It doesn't matter of our setting. Will perform good also when we have few data. And this is something that this paper I'm citing here, Marquisot and colleagues analyzed and show a bit in a paper in WMT last year, where we're trying to see if the differences between languages, scripts, typology, or whatever affect the performance of unsupervised machine translation. They also wanted to check what happens when the two monolingual corpora are in different domains. But because if your corpus is parallel, it's clear that the two languages share the same domain. But in the unsupervised setting, this doesn't need to happen. And also, what's the problem with biases? So if you train in one domain and then test in another, is this technique still useful? So these are things that they analyzed. Let's see the conclusion they got. What they did is take a huge monolingual corpus, mainly the United Nations corpus and Common Crawl, and do different partitions. So for instance, we have for the United corpus, they divided it in two parts. Let's call them A and B. And these two parts don't share any sentence. So we have two corpus that share the domain because they belong to the same domain, but they don't share explicitly the same sentences. And then we have common crawl. That common crawl would be a different domain from the unit corpus. They analyze the performance with BLEU into language pairs, French and English that were supposed, well, there are close languages, and then we have Russian and English that they belong to the same family still, but they are more distant languages. The table here above shows this BLEU score in different experiments. We have what says here supervised. This supervised is the result of a supervised machine translation system trained on the same part of the United Corpus. So AA, same domain, same sentences, everything parallel. Now we use exactly the same data, but instead of training a supervised system, we train this unsupervised system they call this training configuration parallel. So the sentences are the same, but they don't use it in the supervised setting, but in the unsupervised setting. And they observe a drop in Bleu score of around three points for both languages, for Russian and French. So translation quality is not as good as the supervised translation in this case, given the same amount of data. So we lose a bit of information. So yeah, this is somehow expected. Then they wanted to analyze the importance of the parallel data. So they use, for the unsupervised setting, they still use as training data the United Corpus, but in this case, they were training one language with the A partition and the other language with the B partition. So sentences were disjoint in this case. And the drop that they observed was larger. So especially for Russian English, the languages that are most distant, they experiment a drop of almost 6 points. That's the double that they experiment with the parallel data. So we are sharing the domain still here, but data is not exactly the same and the performance is worse. And finally, they wanted to see what happens with the domain is really different. So when going from United Nations data to Common Ground. And in this case, the results are terrible. So if you look at the last column of the table, if you train your unsupervised machine translation system, same amount of data, but different domain, you get almost no translation at all. So Bleu score for Russian is close to 0. Bleu score from French is close to 4. So you are losing 26 Bleu points here. So in this case, what they conclude is that the domain of the data that you are training on is really important. And it's in this case, it's more important the domain than the distance between languages. Maybe this is happening because Russian and English are different, but not that much. If you go to Chinese, it would be more extreme. Yeah, I don't know. One should perform this kind of analysis. But we see that the difference here is very similar to what we saw with cross-lingual embeddings. And then this is the question that they try to answer. Why is this happen? What the domain is so important for the translation quality that one can get with unsupervised neural machine translation? And the answer was cross-lingual embeddings. So if they want to initialize the system with cross-lingual embeddings, what they do is, as we have seen, we have our monolingual corpus, we train our monolingual embeddings, and we map them together. They did this with these configurations that we have seen: parallel, disjoint, different domains, only one corpus, news, only one corpus, and common ground. And they look at the accuracies that these bilingual dictionary inductions were getting, these cross-lingual embeddings. How do they perform? And they saw that the accuracy was more or less the same for parallel and disjoint configurations. But then when they go to the different domains, the accuracy was really bad. In the case of Russian English, the accuracy was 0. They didn't get anything good from these cross-lingual embeddings. And for French into English, it was a bit better, but it was very much depending on the run. So if they run, I think, yeah, it says here, they ran the experiment 10, 11 times to see what was happening. And in some cases, the accuracy was 0. So different domains is a very unstable configuration for cross-lingual embedding. So more than the size of the corpus or the distance between languages, they observed that the different domains is being a big problem for cross-lingual embeddings. And that translates in a very bad quality of unsupervised neural machine translation. So we wanted to answer more questions because we have seen that different domains are important, but how does this translate also in the different languages? So it seems that it's not so different to work with English friends and with English Russian. But in those cases, also the amount of data was quite big. So yeah, if you are using a lot of data, the difference between languages might be easier to solve. When you have smaller amounts of data, everything that makes the learning task more difficult affect the final quality. So there are more things that are important here. What the word order of the languages? Do they have a different typology? Do they share script or not? So all these small things make mapping words embeddings more different. Something that we will analyze, especially later when I talk about self-supervised neural machine translation, is the effect that the distance between languages has in the results. Here, I just want to pull this table that we will see later and look at the column that is in boldface, the one that I'm marking here now. And we see that for these languages that I've shown before, and unsupervised machine translation, the good one, the hybrid one, the one that combines neural machine translation with the statistical machine translation, is not able to learn anything for 5 of the 6 language pairs studied. So we get translation quality measured by BLEU of 0 for 5 languages, and then we get very good translation quality for English Afrikaans. The reason is not clear. We will talk a bit later, but for English Afrikaans, the data set was a bit larger. Languages are quite close. Let me go back to the table again, and we see that the similarity between Afrikaans and English, as measured by some Uriel features, is 0.8. So languages are quite similar. Both of them share Latin script, are kind of fusional, and share some most of the word order. If we go to the other side of the table, we see that for Burmese, the word order is different, the script is different, and the distance between languages is therefore smaller, and the training data was smaller. So all these kind of things affect at the end performance, and this was very important for unsupervised machine translation. So unsupervised machine translation is not able to learn anything in the low resource setting for these cases. We'll see many more examples of this today. Okay, this is what I wanted to do to summarize on unsupervised machine translation. Now that I remember, sorry. Is there any question or any comment before I start explaining some basics on supervised machine translation?
Why would there be a low resource for a language when you're using unsupervised learning? Does that mean you have a small corpus?
In these cases here, yeah, these examples, these numbers that I show here, what we use for training, this is an example that comes later, is trained on the Wikipedia. So we are using the amount of Wikipedias. For all of these languages have English, so the English Wikipedia is huge. But then we have the Afrikaans Wikipedia that is more or less, let's say, a medium Wikipedia, but for instance, for Swahili, the data is very small, or for Yoruba, there are almost no Wikipedia articles. So
that's to be expected though, right?
Yeah, exactly. But yeah, but we want to make the best of the data that we have. For Yoruba or Swahili, it's difficult to get data. So you would like unsupervised machine translation to be able to do what's doing best with the small amounts. And yeah, well, the only thing I wanted to show is that if the amount is really small, it's not working. So yeah, there is no magic here, as expected, of course. Okay, so let's try to see what's happening in the same settings with supervised machine translation. That probably is a strange way to go, starting from unsupervised and then supervised. But let's see how we do here with supervised machine translation. So nowadays, machine translation is approached with as a sequence-to-sequence task. Of course, when you have an input sentence and want to translate it into an output sentence, and the state-of-the-art architecture is as transformers. So you probably have seen this picture a lot of times. This can be the summary of neural machine translation nowadays. So this is the original transformer architecture introduced in 2017. And what we have on the left side of this plot is the encoder. So the encoder receives some inputs here that are converting into embeddings and with some positional encoders. And then they are fed into the encoder blocks, transformer encoding blocks, that in the case of the standard configuration, we would have 6 of these layers, the transformer blocks. The decoder is quite similar. So at the end, what we output is the sentence in the target language, and our decoder has, in this case, in the base form, also 6 layers that has this form here. The difference between encoding and decoding is that in the decoder, you also use information, you use the attention from the words in the encoder. So you have an additional layer inside each of the blocks. And another difference that you have is that at decoding, for encoding, you can use the information on the whole sentences. At decoding, you have something that is called mask attention, because you cannot use the future to predict your words. So when decoding, you only have information of the words in the moment of the sentence you are decoding. Let me just zoom in one of these blocks, because these transformers blocks, I saw them as the summary of all in NLP done last year. So everything done for NLP was based on using a transformer, a divert or whatever to solve a new problem. And the basic of a transformer is quite simple, even I don't think it's intuitive at all, but the idea is that you get your input and divide your input and the embeddings in 3 different matrices. So each of your words has 3 different weights associated. One belongs to what they call query, key, and value. So you decompose your input word into these three matrices, and then do the attention mechanism on these matrices. That's mainly an scale dot product, concatenate the output, and then you have the output of your input here. So you do intra attention for all of these words in each of the transformer layers, at the encoding and at the decoding part. So probably we don't need to understand the details what is going here, but I'm just showing this because some of the parameters that we will need to learn in our system will be related to this. Will be related to the numbers of layers that we have in our transformer blocks, also to the number of transformer blocks that we have in our encoder and the decoder, and then it's also important the dimension of this key, phi, and k matrices. This is the dimension of our system, and the number of heads that we have in each of the attention layers. So these are important parameters to tune later on in neural machine translation, and all of them are related to this self-attention and transformers. So which are the results that neural machine translation with this kind of system achieves? Of course, there is not only this transformer model, there are really lots of variations of it, different ways or modifications to do the training, either at data level or at architecture level, and different number of layers, different small modification on attention. And in most papers showing these architectures, there are different, you can get improvement 2-3 points of play going from one system to the other, or testing on different test sets. So, but most of them are based on this basic architecture of Pleo. So I'm not going to go to the papers that do this and with this model variation. I'm just interested to see which is the translation quality that any of these variation of the transformer can achieve in current state-of-the-art machine translation. And to do this, there are two nice evaluation campaigns that take place each year to see the quality of the state-of-the-art of machine translation. One is WMT and the other one is IWSLT. And one of the interesting characteristics, especially of WMT, is that the translation quality is not measured by automatic metrics like BLEU or comment, but with manual assessments. So people submit the systems, we have their translations evaluated, and these translations are evaluated by humans using direct assessments. Direct assessments means that a person sees the translation of a sentence. When it's possible, the sentence is seen in context and also with the source language. Sometimes this cannot be done as complete because of lack of evaluations, but this is the best case scenario. You have a person looking at a translation in its context and also with the source or original sentence. And then people need to grade the quality of the translation in a scale from 0 to 100. If you do this with hundreds of people, then you have a good estimation of the quality of your translation system. And we will see now the results that we have for the WMT task last year, because the evaluation campaign for this year is just taking place now. So we don't have the results yet, but they will be soon out in 1 month or two. We will see what's happening this year. So we will know by the end of our series. What happened last year? So last year, the evaluation was done in about 8 or 10 languages pairs. I don't remember now, but the best translation quality was achieved for English German. This average score that we see here is the average of direct assessments, this scale from 0 for 100 for all the evaluators that saw these sentences. And you see that we have some things for the best systems that are close to 90. So yeah, that means that the evaluator sees that the translation quality is really high. It's really very close to perfect. We see here several systems that were submitted. And what we see also in the middle of the list is 3 systems that are called human. These are not really systems, these are the reference translations that they have to the evaluation. So these are translations that were done by humans. And you see that the quality of the engines is so high that the ranking by humans put some of the systems, this Oppo and Toku, for instance, higher than human translation. So this human A translation is worse, according to humans, than some of the machine translation systems that exist nowadays. The best one was still one of the human translations. So, and the statistical significance was here more than 95%. I think that was the threshold. So humans were better than machines, yet still for this task and this test set. If we go to the other direction, German English, we have the same with less participants, and something interesting happens, that is that the best translation is now a system Voltran. So humans, the reference that they have for these language pairs score lower than the best system. You see that all of them lie in the same block. That means that the statistical significance was not happening here. All of them are close enough. So the conclusion here is that translation quality has achieved a point where for supervised translation, rich language pairs with lots of data, we can achieve the same, more or less the same that a human can achieve, at least under these settings. And in this case, what we have is relatively close languages. So German, English are quite close. But the difference with what's happening with Japanese English is not that different. For Japanese English, they still have a lot of data, not that many, but big corpus still, I think it was like 20 million parallel sentence, something like this. Languages are distant here. English and Japanese don't have a lot of similarities. But if you look at the average of this direct assessment score, translation quality is above 70 and close to 80 in some cases. So according to human translators, the translation quality is still very good. The performance of humans could not be evaluated in this case for Japanese English, probably of lack of evaluators, I don't know. But if we look into English to Japanese, we see that in this case, translation quality from humans is better than neural machine translation. And it's better significantly according to the statistical test, but we are not that far. So if human translation was scored with 79.7, we have the best neural machine translation that scores 77.7. So translation quality, even for distant languages, is getting very, very good. I wouldn't talk about superhuman performance yet, because this is a specific test set, a specific language pair, a specific characteristic, but it's clear that translation quality is really, really very good. And what's happening with languages with less resources and distance? So this is still WMT. So this is distant languages, of course, less resources, but not really low resource. I think that the language pair with less resources had about 4 million parallel sentences. So that's really quite a lot of sentences for neural machine translation, not to get super high quality, but already to learn something about the languages. And in these cases, we see that translation quality, even for distant languages, again, is relatively good. The best system for English grammar, I don't know how it's pronounced, is close to 80, also 77%. Lower for Pashto, it drops 4 or 5 points, and a bit worse going into English. What we see here is that the language pair is difficult, and it's difficult not only for machines, also for humans. So if you see here, humans are not getting a performance or 80% of quality or 90%. So humans are also in the middle of the table with 73 here and 79 here for direct assessment. So translation is more difficult. Humans can even perform not as well as expected, and the evaluation is also more difficult. So what we have seen now for supervised machine translation in the hard result setting. So we are using deep learning models, and deep learning models needs a lot of data, but when they have this data, the training gives very good performance. So we see that in the high resource setting, translation quality is very good. When it's not that good, it's something that is difficult, and humans are also struggling getting good data. But another thing that we would need to take into account is the importance of learning the parameters properly. So a neural machine translation is, of course, a machine learning problem, and as all this problem, we need to do parameter tuning. The problem with neural machine translation and other deep learning tasks is that we are using huge amount of data, and trainings are really very slow. So if you have, I don't know, 10 hyperparameters you would like to explore, and your training for English German takes 1 week, it's clear that you cannot explore all the parameters in the way that you would like. So, and that's a general problem that face lots of deep learning architectures these days. That the hyperparameter tuning is really expensive and really very slow. The good things is that neural networks are able to learn in even very bad circumstances. So maybe your hyperparameters are terrible, but you have so many data that your system is still able to learn good models. But this is not happening for low resource neural machine translation. So one of the premises that you expect for deep learning is to have a lot of data. Of course, in the low resource setting, you don't have lots of data. So in that case, this parameter tuning is really crucial. So you need to do it very carefully in order to be able to take the most of your network. The good side is that in the low resource setting, you also don't need 1 week to train a system. So you can expend a bit more resources. So instead of 1 week, maybe you just need some hours to train a system. And in that case, the hyperparameter tuning might be even feasible. One thing one cannot do or one should not do is deal with low resource neural machine translation as it was high resource. So I see how English-German works. So I take the parameters that I use for English-German into my Yoruba English data set with very few data and expect that it performs as well as it was doing in the low resource setting. This is not working well at all. And this is one of the reasons why at the beginning, people was saying that it's better to use statistical machine translation when you don't have data and not use neural machine translation because it's performing worse. Because statistical machine translation is quite stable and hyperparameter tuning is very fast and translation quality is relatively good also with a small data. But yeah, some analysis clearly show that this is not the case. The best thing to do even in the low resource setting is stick to neural machine translation. They still really work quite well when they work, and try to tune your system. So let's see some examples of the importance that this has in low resource neural machine translation. A few years ago, and this work from Cohen and Knowles, this was at the beginning of the transformer architectures where translation quality for neural machine translation was starting to be really very high. And this work tried to summarize what were the challenges for neural machine translation, what were the things that could be still be done to improve neural machine translation and still a bit more. And one of the most important things they noticed is the importance of the amount of training data. This plot on the right says exactly the things that I explained in the previous slide. So this is the translation quality measured by Bleu for Spanish-English translation system when you change the size of your corpus. So, and the x-axis is in a logarithmic scale and it's showing the amount of words that we have in the English part of the corpus. So ranging for a less than million words to billions words. So all this scale is really low resource. So I said that the less resource language pairing WMT last year had about 4 million parallel sentences. And we are talking here about words. So and now we are considering less than 1 million words. So really very small corpus. And what we show here is that neural machine translation was performing really bad when the data was small. This is the green curve here. So for sizes around million parallel words, the translation quality was terrible for neural system. And then they did the same training with the statistical systems and they saw that it was more stable. So the difference in translation quality was 15, 20 Bleu points between neural and a statistical system. But they didn't bother at that point to see what happened with these hyperparameter tuning. And this is something that was done a couple of years later by Sanjit and Sang, when they saw really the importance of this kind of training. And they did a similar thing. In this case, it's not Spanish English, it's German English. And they used two systems, the very low resource setting with 100,000 words and a slightly higher setting with 3 million words. Both of them could belong to low resource setting, but it's clear that 100K words is really very few for neural systems. So they did the same, train a standard phrase system, a standard NMT system without anything in additional. And they saw that where the data is very small, these 100K words, and the neural system was not able to learn anything. Exactly the same that we have seen before with unsupervised training. We couldn't learn anything with so few words. So the difference here was 16 blue points. When we increase a bit the data, the neural system already performed close to the phrase system. But this was mainly a problem of a bad hyperparameter tuning. So they did a first system where they use what they call mainstream improvement, that these are some techniques to better regularize the training. So they use tight embeddings, some dropout, layer normalization, level smoothing, some techniques that are nowadays used in all the transformer architectures that people is using. And with this, they get an improvement of 6, 7 blue points in both cases. In a case when the translation quality was already more or less decent, but also in the low resource setting when the translation quality was 0. So only using better ways to do the training, they got this improvement of 7 blue points. But as I say, this is general. This is general for the low resource setting and for with cases with slightly more data. Not high resource, but slightly more data. But they noticed some important parameters that need to be taken into account in the low resource setting. So in the low resource setting, one thing what we need to notice is that we don't have data. So we cannot learn all the parameters that we would learn in the standard case. So we need somehow to reduce our networks. And one way to reduce the network and the thing that performs best is reducing the vocabulary that one used. In the high resource setting, maybe one would be using a vocabulary of 40 symbols. And they saw that in this extremely low resource setting, if they reduce the vocabulary to 2000 symbols, really very small, translation quality improved a lot, already by 5 points. This is something that you cannot do in the high resource setting. It makes not sense to try to only learn 2000 words in that case. Other things that also help in the same idea, not reduce only the vocabulary size, but also the batch size, which is not that important in the low resource setting. And then we have another family of methods that also help improving the low resource setting, but these are also things that help a bit in general, even they help more in the low resource setting. And this is mainly trying to add noise via dropout or whatever techniques to your training. So if you do aggressive drop out in your training, you gain again 3 blue points here. Then working on learning rate, level smoothings and small things, you can even gain a bit more improvement, one point here. But the important thing to notice here is that by properly tuning your network to your explicit problems, seeing what are the things that make a low resource setting difficult, you can go from a blue score of 0 to a blue score or more than 16. So, and the difference in the case when you have more data, it's also important. You improve 7 points, but it's especially relevant in the very low resource setting. So lesson learned here. Neural machine translation can still be used for machine translation, even if you don't have data. So what you need to do is work more than in the whole resource setting. You need to really do some hyperparameter tuning and look the best way to optimize your system. And this is important as this is a machine learning problem. So this is something that you should be doing always. But of course, doing this does not exclude all the other techniques that can be applied to neural machine translation. So other things that we have been doing before in several other experiments is data augmentation. We have seen back translation, for instance, that it's the main ingredient for unsupervised machine translation. Of course, you can also do it here in self-supervised. You can use pre-trained models to initialize your networks. And yeah, this also gives really very good results. This is something that we will talk later. And you can also approach your low resource problem via multilinguality. And this is the thing that I want to talk in the following. What happens in multilingual supervised system, and how can we use multilingual systems to improve low resource machine translation? So some things that we already know. Machine translation is in some way multilingual by nature. It's at least it's a bilingual task. You have a source language and a target language. Another thing that we already know is that machine translation includes the semantics in vectors. So we have our word vectors at the beginning of the encoder and at the end of the decoder. In the middle, you have all the outputs in every layer of the transformers that give you word embeddings and sentence embeddings when you concatenate. And this is something that reminds us on word embeddings, right? So we have inside our machine translation system, we have our particular word embeddings here. To make it multilingual, we'll see that the extension that we need to do is really straightforward. In the easier and more simple approach, we will have a shared encoder for several languages and a shared decoder for several languages. Still, semantics will be encoded in vectors, but now these spaces will be multilingual. And this is something that reminds us to cross-lingual weight embeddings, right? We have several languages in the same space. In this method, we don't need to do the projections before training, but in principle, a multilingual transformer would be learning these cross-lingual embeddings in a natural way. And this is what we want to explode with multilingual neural systems. And how do we build them? There is a way very simple to learn a multilingual machine translation system. So for training a standard English to German, let's say bilingual system, what we would do is we would have our engine, the transformer in this case, or whatever translator engine that we want to do. And the only thing that we need to do is feed it with parallel corpora because we are in the supervised setting. So for going from English into German, we would feed the system with a corpus of parallel sentences. Here, for instance, the English sentence would be traveling around the world, and the system would need to learn that the translation is Reisen, if I'm not mistaken. And we will feed the system with several sentences. I love hummus, ich mag hummus, and whatever. So this will help us training an English to German neural machine translation system. What can we do if we want to do it multilingually? So, okay, now I have my English to German, but I want also to translate Catalan. So I want a system that translates from English and Catalan into German. That's simple. The only thing that I do is during training, I add more sentences. So now I've been feeding the system with English German. So let's add also Catalan German sentences. So in the same corpus, I would add the equivalent sentence, m'agrada l'hummus, ich mag hummus. So in this case, the system will learn to translate for a big language that for the system is not two different languages at this point. We have a Catalanglish, or how do you want to call it? We would have a language that is the concatenation of the vocabularies of the two languages. And the system will always learn how to translate all this into German. So this is the most easiest thing to do multilingual translation, just mix the data. What happens if we want to do from many languages into many languages? So if you want to do English Catalan into English German, so we do the same. we add more sentences, we add all the language pairs. So in this case, we would also need sentences Catalan into English. For instance, m'agrada l'hummus, I like hummus. The only thing we need to add here is that since at least till now, transformers cannot guess our will, we need to say into which sentence, into which language do we want to translate the sentence. So in this case, since we would have Catalan sentences that map into English and Catalan sentences that map into German, but what we need to do is annotate our input data with the attack saying the language we want to translate to. So when the decoder has different options to translate, different languages to translate, we need to tell the decoders at least which language we'd like to translate into. So this is the only difference that we need to do for multilingual systems. Just put corpus from different languages together, and in case of ambiguity, help the system to learn which language it should be translated into with the addition of these tags. Why should this be working? First, because we are in a deep learning setting, we need a lot of data. Multilinguality helps adding a lot of data. So in this case, we will have larger corpora. And this will be useful. It will be useful principally because languages share more vocabulary than we imagine. So there is a lot of vocabulary that is shared between languages. In the examples that I've written before, the word humus was very similar or exactly the same in Catalan, English, and German. So this, and remember that when we were mapping cross-lingual word embeddings, these kind of dictionaries or anchor points were really very important to put all the languages in the same space. So while adding multilinguality, we are helping the system to map everything together and to put all the languages in the same space. And this is something that, and with my intuition at least, it should help the system to learn to translate. And this is true in the high resource settings where we have full words or almost full words. But remember that we saw like that for the low resource setting, one of the improvements that we could do is use a small vocabulary. So use very few BPEs transformation. The smaller the vocabulary, the more shared vocabulary will be. It's not clear if all the small BPEs share meaning, because at some point you are just comparing two letters. But since a small BPE works, it's at some point this means that they share some semantics. So in the low resource setting, joining different languages is going to help you to have a shared vocabulary, and having shared vocabulary helps learning the final translation task. Another motivation to use it, I mean, why not? It's really very simple to implement. I don't need to do anything. I don't need to check if it performs better or not than the bilingual content part. And also, under a practical point of view, if you need to translate from among 10 languages and you train one multilingual system, you only need to worry about one system. So you only need to maintain one and do all the translation with that system. Otherwise, you will need to keep and maintain all the n per n-1 models that you will need to generate. And I've talked about very simple case of multilingual neural machine translation, but there are a lot of different architectures, and some of them very, very complex architectures that have different encoders and decoders per language. And then the attention is designed so that it only takes care of close languages to share parameters or whatever. So there are really a lot of different architectures, very complex architectures that are able to perform very well in the multilingual setting. But this is somehow out of the scope of today's talk. So, but if you're interested in multilingual neural machine translation, there is this survey here, this survey written by Davy and colleagues last year, when you can see lots of applications, lots of systems, and the comparison between all the use cases that they analyze. Just to notice that they divide the use cases where multilingual neural machine translation is useful, and one of the important one is low resource machine translation. So it's one of the architecture that is helping in getting good quality in the low resource setting. And one thing I want to also show is this arrow here that goes to zero-shot modeling. And what's the meaning here? It's meaning that when you train multilingual systems, you can even try to translate languages for which you don't have parallel data. So in the previous case I said before, I was feeding the system with Catalan and English sentences in the source, and in the target we have English and German sentences. But I didn't have the combination Catalan-German, I think. Not all the combinations, but made possible. When you do multilingual translation, you can even be able to translate languages that are included in your system, but not in a direct way. So languages for which you don't have parallel sentences. And this is what you call zero-shot translation. So should we go multilingual? In general, after analyzing several systems, one sees that if you have a multilingual system that shares different languages, what you get is an improvement for the low resource language. So if you have English, German, Yoruba, and Russian, maybe for English, German, you will get worse translation quality that you will have with the bilingual setting, but you will be getting improvement from Yoruba, for instance. So should I use it? Use it depending on the problem you want to deal. So it's not always good, but it might be something good in the high resource setting. It's almost always good in the low resource language, even in cases where languages might be different than your high resource content. This is one of the motivations to use multilingual architectures, that they are useful in the low resource setting. And there is another one, and that is one of the goals that we wanted to achieve today, talking about self-supervised neural machine translation. Self-supervised neural machine translation, we'll see that it's based on the behavior of multilingual systems. So let's see this behavior of multilingual systems that will be interesting for us. So, as I said, machine translation is at least a bilingual task. So it's from the beginning is very close to multilinguality. We've seen that it encodes semantics in vectors. And we have just seen also that going multilingual can be very simple. We just need to append a tag at the beginning of the source sentence when we want to remove ambiguities towards which one language to translate into. Otherwise, for the system, is just having the same architecture that deals with a language with more vocabulary, so with more distinct words. There is nothing else that differs the bilingual case from the multilingual case. So now, if you do this, all the languages will be in the same space in the decoder and the decoder. So all the languages will lie together. But how are these languages distributed in this space? And the distribution is useful for us. And this question, and I ask this question because two things before looking at the results, two different things could be happening. It could be the case that that the system learns to differentiate languages, so that if you look at the embeddings in your space, you see clusters of words that belong to English, clusters to words that belong to German, or that the system learns to cluster together sentences that have the same meaning. So the same sentence in English and the same sentence in German would lie together because they have the same meaning, and this independently of the language. But which of the two options is happening? So let's see a first example. In this example, we have a multilingual system. This multilingual system is trained with TED Talks in 5 languages. So we want to build a multilingual system that is able to translate between German, English, Dutch, Italian, and Romanian. So in 5 languages, we train with a combination of languages in the 5 pairs. And then after training, we look at how sentences lie in the space. What I have done here is I've selected, I think it's 8 sentences. Let me see, yeah, 8 sentences. These were the top 8 sentences of the test set. And then I look at the sentence embeddings that these 8 sentences have in all the languages. And then we plot the representation that we have. And we see that if each color is representing a different sentence. So we see clearly 8 clusters of sentences. So the system after training has learned to identify semantics. So for instance, on the top right, we have this green color here that belongs to a sentence, and the same sentence we have it in Romanian, Italian, Dutch, German, and English. So clearly, sentences are not separated by language, but they are separated by semantics. Yeah, maybe it's difficult to see it here, but also at smaller detail, we can see, for instance, that Romanian and Italian are closer than Romanian and English, for instance. So there is a bit of clustering of language, but looking at this, it's not really relevant. So semantics are clearly distinct after training a multilingual system. And that means that if you want to translate something from German into Italian, maybe the sentence in Romanian can help you to do the translation. And this is why multilingual neural machine translation allows you to get good performance for low resource settings, because languages that don't really have a lot of data can be helped by the languages that lie close together, close enough. But this case can be seen as a very ideal case, because we were using 5 languages in the TED Talk corpus. So we have the same corpus for all the languages. So it was quite homogeneous. The size for all the languages was also the same, because the corpus is the same. And the domain is really very similar, even if it's not parallel for all the sentences. So the similarity between the data is really high. This is what we have seen before with unsupervised neural machine translation. This is the case where unsupervised machine translation was working best also, when all the data were of the same domain here. So let's see what's happening when the problem is a bit more challenging. So we can do the same with other languages. In this case, we were using English, Spanish, and Arabic. And the corpora is heterogeneous. Before we were using a small corpora, but everything was TED Talks. Here for English, Spanish, and Arabic, we will be using different corpora, United Nations, News, Cromwell Crowd, whatever, very different and heterogeneous corpora. And we try to make the sizes of the final corpora more or less the same, but also it's not exactly the truth. So data is not parallel. We have heterogeneous. For some cases, we have more examples. So the corpus is not as clean as the corpus that we have before. So this is a more difficult problem, and we want to analyze what's happening here in more detail. So the idea here, the dots that you see are still similar things. Same color means same sentence in different languages. So for each color, we have 3 dots, one for English, one for Spanish, and one for Arabic. And you see that things are closely related to other colors. And this is because here we wanted to analyze the effect of similarities between sentences. So let me show you with the example sentence, what do I mean here? These are the sentences that are plotted in the previous plot. We will see this again. So the first top 3 sentences are these triple one here, sentence 1, sentence 2, sentence 3, belong to the first triplet 1, when we have exactly the same sentence in English, in Spanish, and Arabic. So these are the 3 black dots that we will see again in the plot. Then we will have two triplets here, the ones that were dark blue and light blue. So we have 6 sentences, 2 English, 2 Spanish, 2 Arabic. And if we look at the English one, we see that they are really very close. So you don't need to worry and you don't have to worry. These are very similar sentences. And we add things like this because what we wanted to know is how are these sentences encoded at the end? So what's closer? Sentence 4 to sentence 5, small variations of the same sentence in English, or sentence 4 and sentence 6, exactly the same sentence in 2 different languages. So this is a question that we want to answer next. More examples. The next 2 triplets here are similar to the previous one, but in this case, the similarity between the sentence is slower. So we still have 3 sentences, 1 per language, but if you look at the English example, we have one of the sentences is Mandela's condition has improved, and the other sentence is Mandela's condition has worsened over the past 48 hours. So sentences are similar, but the meaning is not exactly the same. So we expect these sentences to be farther away. And we want to answer the question to see if we will be able to detect that this is happening. So we will be able to detect that these sentences are not exact translations, one of the other. And finally, we will see also in the pictures on orange and brown sentences. In this case, sentences talk about the same topic, but the semantics is even more different than the one before. So for triplets 6 and 7, we have an example that says, vector space representation results in the loss, blah, blah, blah. And the other is, if a term occurs in the document, blah, blah, blah. So in both cases, they talk about mathematics somehow. There are similar vocabulary. They talk about terms and about vectors, but the semantics of the sentences is more different. And the same, we have the sentences, the 2 sentences in English, Spanish, and Arabic. So yeah, remember the colors. So we go from black to the bluish one, the greenish and yellow, and then the orange and brown, according to the similarity that we have between the sentences. We go back to this plot with the colors to see what we remember. And we see, for instance, that the black sentences, the ones here in the middle, lie more or less close together. Then we have the second block of sentences here, the blue sentences, that sentences were really very close in semantics. So 4 and 5 was the same sentence, just with this small variation. You don't need to worry and you don't have to worry, and they are really very close in space. And then the other language, for example, from S5 to S7, the language is encoded farther than the same semantics in the same language. So we are somehow seeing some language clustering here. But even if we see this language clustering, semantics is stronger than language clustering. We go to the greens and yellows, the dispersion is a bit larger. We go to browns and oranges, and the dispersion is even larger. So the more the semantic difference between sentences we have, the more dispersion we observe in the projected semantic space for all the languages. Finally, one thing to notice here is this shaded version here. This shape here includes all the points that belong to Arabic. So we see the importance of language clustering. So all the Arabic sentences are in the same space together, and then English and Spanish are a bit more distinct. So this might be related to the difference between languages. So Arabic is more distant to both English and Spanish, that English and Spanish are among themselves. So we see here still the clustering of the Arabic languages. Can this still be useful? Yes, this is useful, and this is because the semantics are still very strong, even if we are not in the ideal case of TED Talks. A way to see it is let's just use our system to translate sentences in different languages, okay? So let's take a data set. We are using the STS data set in Arabic, English, and Spanish. And we use our multilingual system to translate the sentences for each system. And we look what happens among the languages. So we use this system and translate sentences. Let's start with the Arabic subset. So we take sentences in Arabic and use our system to translate it into English and Spanish. And now we compare the similarity between the translation in English and Spanish. So we compute cosine similarity here between the English sentence and the Spanish sentence. And we see that the cosine similarity is close to 1. So the similarity between the two languages, the average similarity of all the test set is 0.97. We do the same with the English corpus and with the Spanish corpus, and we see that similarity is always very high. It's a bit lower for English and then a bit lower for Spanish. And this shows again the differences between languages. Arabic English might be farther than English Spanish are. So the closer the languages are, the higher the similarity. The farther the languages are, the lower the similarity. But still, in all cases, the similarity between languages is really very high. We have done the same not only with Arabic, English, and Spanish. What we see the same trend when we train a multilingual system with German, French, English, Spanish. Languages here are slightly closer together. The corpus is still heterogeneous, so the difficult training condition. And then we compute all the similarity between all the language pairs. And we see that in that case, the similarity is even larger. So we are really close to 1 in all the cases. And there are some marks here, some asterisks here in some numbers. This just means that for these numbers, we didn't have direct parallel data. So we are comparing in this case, what's this? This is French-English translation, and we didn't have training data German to French, for instance. So this is a comparison when not all the languages were covered. And even in this case, similarity is really high between languages. So this is a first indication that we can use similarities obtained by neural machine translation system to try to help itself. And this is what we will see. So what's the takeaway point here? So that in multilingual neural machine translation, related languages cluster better together than distant languages, that the nature of the corpus also affects the clustering. So plots are not so nice in the challenging test set with Arabic, Spanish, English, and in the multilingual TED Talks test set. But this is not something that we see in the first time. So we have seen also the same with word embeddings, with multilingual mappings. It's always the same in natural languages. So related languages and same domain are easier tasks than distant languages and different domains. So this is what we are seeing in all the cases. So, and this is happening when you use a multilingual neural machine translation and you train them. But is this the same during the whole training? It's not exactly the same. So the system is going towards this behavior, but it's not that different. So this is the plot on the right is the thing that we have been looking in detail before. And the plot in the beginning is what you have at the beginning of the training. At the beginning of the training, what you see is a higher clustering per language. So everything in Arabic, this shaded region, it's smaller. So that means that Arabic was very clustered together, and then it started to expand to try to cluster semantics afterward. So there is like a trade-off. At the beginning, languages and very close sentences form some kinds of strange mapping. And the training, what it's doing is trying to solve this and trying to do really a clustering by semantics and not per language. So this is what the system is trying to do. It can be done better or worse depending on the data that you have. But this is the method that the internally neural machine translation is using to learn machine translation. And the point that we want to use in self-supervised machine translation is exactly this. What we want to know is the system able to distinguish between parallel sentences and non-parallel sentences? This is not a problem in standard neural machine translation because everything is parallel. But remember that we wanted to translate also with monolingual data, for instance. So in this case, there must be sentences that are parallel and sentences that are not parallel. So the system would be able to distinguish them. So let's see what's happening. And we divide our data in three different kind of sentences. Translations. These are sentences that in our test set have the highest similarity 5. So this would be really translation. We have sentences that have nothing to do. So these are the sentences that in our test set are tagged with a 0. They have similarity 0. And then we try to use very close related sentences as the ones that we saw in the example, that are those sentences that are in our corpus, they are tagged with similarity 4. And let's see if the system distinguishes between this kind of sentences. At the end of the training, we see that, okay, these are the columns, the similarity between pair of sentences between Arabic, Arabic, English, English, Arabic, English, Arabic, Spanish, and English, Spanish. It is clear that in the first two cases, we don't have translation, it's a monolingual setting. So let's look at what happened in this multilingual setting. So for the translations on the corpus, we see that the average similarity in our corpus is 0.6 with uncertainty of 0.7. And for unrelated sentences, non-translation, the average similarity is 0.3. So the difference between translations and non-translation is big enough so that the system can distinguish them. And this is the same for Arabic English, for Arabic Spanish, and for English Spanish. So at the end of the training, we are always able to differentiate translation from non-translation. And what happens with similar sentences, sentences that are not translations, but are really close to each other. So in that case, we see that the similarity between these sentences is slightly lower than for translation, but we are not really able to clearly distinguishing. So when trying to separate between translation and non-translation, we will be also gathering some sentences that are similar to translations, but are not really translations. We will see later if this is good or bad for our training. And now, for now, we only know that this is what's happening. And I will finish with this because we are all very close to the ending the time. So this is something that happens not only at the end of the training, but also from the very beginning. So the first block shows what's happening after only 1/10 of epochs. And we see that the difference between translation and not translation is already detectable. So the similarity is of 0.2 in this case with a variance of 0.1. So already from the beginning of the training, we seem to be able to distinguish translation and non-translation. And this is something that we see in multilingual neural machine translation. This is a standard. This is what happened in a supervised setting. Can we profit from it? And this is what we will see next time. This is just what self-supervised neural machine translation does. So what does self-supervised neural machine translation? We see that the neural machine translation embeddings are able to differentiate translation from non translation very soon at the very beginning of the training. So what happens if we don't fit the supervised setting with parallel sentences, but exactly we do the same with no parallel sentences, with a mixture of both translation and non translation? Will we be able to use only the right data? And the answer is that yes, it can. So we will see next time how self-supervised neural machine translation is doing this. So the main idea is that we will use exactly the same architecture. We will be using a transformer in the examples that I will show, but the difference is that I'm not giving a parallel sentence corpus when I have sentence A and sentence B exactly the same sentence in two different languages, but I will be given to the system, for instance, the Wikipedia in English and the Wikipedia in Spanish. And I will ask the system just to find which sentences are good to train on and which sentences are not good to train on according to the internal representation that it has. But yeah, we will start next section with this, and we will see how we can perform translation quality. I just wanted to give a spoiler because this is the last table that we have that I showed at the beginning for unsupervised neural machine translation when we saw a lot of zero here. And this block here will talk about self-supervised configuration. And we see that we are able to go a bit better than unsupervised machine translation is with self-supervision. And we go from all zeros, we will have this both column here when we are able to achieve something even higher than 10 for some languages. We are not able to do something for other languages, and yeah, just to get something a bit translated for all of them. But yeah, we'll see this next time. And I'm again late, a bit late, not that at the last time, but already late. But if anyone has any question, is more than welcome. Let me try to see if I can see you. Okay, so if there are no questions, then we can see something in the chat. Yeah, so maybe if we don't have more questions, thank you everyone for attending today to the talk. This morning we have uploaded the slides of the first two sessions. So yeah, if you're interested in seeing something, I think they are already slides. And as always, if you want something, just send me an email and I can share more information if needed. So yeah, see you, I think, in a couple of months now. We have the summer break in the middle. See you.
Bye-bye. Thank you.
Thank you. Bye.
Thank you. Bye.